Welcome to this video on signals and its classification, focusing on fundamental concepts and properties. Signals and systems form the foundation of modern electronics and communication. Nearly every device we use, from smartphones to medical imaging, relies on processing information through signals. Understanding how signals behave is crucial for engineering future technology. A signal is a measurable physical quantity that carries information. Mathematically, it is a function of one or more independent variables. Examples include voltage in a circuit or acoustic pressure in speech. The primary purpose of a signal is to represent and transmit information across a medium. Whether it's a temperature sensor reading or a radio wave carrying a digital broadcast, the signal is the physical embodiment of the message. Signals depend on independent variables such as time, the most common variable in electrical engineering. Signals can also depend on space, like the X, Y, and Z coordinates used in image processing. In one-dimensional signals, like audio or an ECG, the signal depends solely on the time index. A time-based signal can be continuous or discrete, which means it is sampled at specific intervals. Spatial signals, such as photographs, are defined over coordinates. A digital image is a two-dimensional signal where the amplitude represents light intensity at a spatial location. Spatial signals allow us to process patterns, textures, and visual geometry. Signals can be represented mathematically through equations, which are precise and useful for theoretical analysis. They can also be represented graphically as waveforms plotted on an axis, which is intuitive for observing trends, peaks, and noise. A system is an entity that processes input signals to produce output signals. It performs a specific transformation or operation. Examples include an amplifier increasing signal amplitude or a filter removing unwanted noise. The system acts as a mapping or transformation, $T$. The output signal $Y of T$ is the transformation of the input signal $X of T$. This process converts the input excitation into the output response. The input signal $XT$ is the external stimulus applied to the system, often called the source signal. The output signal $Y of T$ is the resulting signal after processing and represents the effect of the system on the input. We now move to Part 2, Signal Classification. Here we will categorize signals based on their fundamental properties. Time-based classification divides signals into continuous time, or CT, and discrete time, or DT. Continuous time signals are defined at every instant, while discrete time signals are defined only at distinct time instants through sampling. A continuous time signal, $XT$, has a continuous independent variable, $T$. These signals occur naturally, and for any 2 points in time, there is an infinite number of points between them. A continuous time signal is visualized as a smooth waveform without breaks or jumps in the time domain. Examples include analog audio recordings or the voltage from a battery over time. A discrete time signal, $X$, is represented at integer sample indices, $N$. It is the basis of digital signal processing. A key property is that the signal is undefined between sample points $N$ and $N plus $1. Discrete time signals are represented as a sequence of values. Visually, we use a stem plot, where vertical lines show the amplitude at each integer step, $N$. Next, let's classify signals by amplitude. Analog signals have continuous amplitude, offering high resolution but sensitivity to noise. Digital signals have discrete amplitude levels, defined by quantization. An analog signal is continuous amplitude, where information is directly proportional to a physical variable. Examples include sound waves converted to voltage by a microphone, or the mercury level in a thermometer. Analog signals have infinite possible values within their range. This richness makes them challenging to copy perfectly without introducing noise, often leading to signal degradation during transmission or storage. A digital signal uses discrete values. It is essentially an analog signal that has been sampled in time and quantized in amplitude. Modern computers operate exclusively on digital, binary signals. Digital signals have finite levels. This, quote, staircase behavior is advantageous because it allows for error correction and enables perfect replication across digital networks, ensuring data integrity. Signals can also be classified by predictability, deterministic or random. Deterministic signals are predictable and described by a formula, while random signals are unpredictable, requiring statistical description. A deterministic signal's value at any time $t$ is perfectly known, with zero ambiguity about its future behavior. These signals are entirely characterized by an explicit mathematical function. Predictable waveforms like sine, square, and sawtooth waves are deterministic. If you know the formula and initial conditions, you can calculate the signal's value at any future time with certainty. Random or stochastic signals contain inherent uncertainty, making it impossible to predict their exact value. Examples include thermal noise in electronics or atmospheric interference affecting communication. Random signals are described statistically using properties such as mean, variance, and probability density functions. This analysis helps determine their impact on systems. Finally, signals are classified by repetition as periodic or non-periodic. A periodic signal repeats its pattern, satisfying $x of t equals x of t plus $t, while a non-periodic signal does not have a repeating pattern. A periodic signal repeats a fixed pattern indefinitely, defined by its period, $t$. Common examples are the AC power line voltage or simple oscillating waveforms. The fundamental period, $t_0, is the smallest time duration after which the periodic signal exactly repeats itself. It is a critical parameter in analyzing repetitive signals. A non-periodic signal, also known as an aperiodic signal, does not repeat. These signals often describe one-time events or transients, such as a single lightning strike. Aperiodic signals have an irregular pattern. Mathematically, they can be viewed as periodic signals with an infinite period. They are typically analyzed using the Fourier transform. We now move to Part 3, Signal Size, where we measure the strength of signals using the concepts of energy and power. A signal is an energy signal if its total energy, $E$, is non-zero and finite. The equation shows how energy is calculated by integrating the square of the signal's magnitude over all time. For an energy signal, the average power, $P$, must be zero. This is because a finite amount of energy spread over an infinite amount of time results in zero average power. A signal is classified as a power signal if its average power, $P$, is finite and non-zero. The calculation of average power is defined by the limit of the average energy over an increasingly large time interval. For a power signal, the total energy, $E$, is infinite. Periodic signals, which continue indefinitely, are typical examples of power signals because their energy accumulates infinitely over time. The formula for calculating energy involves integrating the squared magnitude of the signal over time. For complex signals, the magnitude squared is found by multiplying the signal by its complex conjugate. Power is calculated by finding the average energy over a specific time window and taking the limit as that window goes to infinity. For periodic signals, the power over one period equals the average power over all time. Graphically, an energy signal, like a pulse, is localized in time, so the area under its squared magnitude is finite. A power signal, like a constant sine wave, continues forever, resulting in infinite energy but constant average power. In summary, we covered signals as information carriers and systems as processors. We classified signals by time, amplitude, predictability, and periodicity. Finally, we categorized them by size, using finite energy versus finite average power. Understanding signal types and system transformations is essential for modeling, analyzing, and optimizing the complex communication networks that power our world.